So we actually have two demos here, both with Knights Ferry. In one case, we're doing a simple 18-line program that we can run either on a Xeon or we can run it using Knights Ferry, unchanged. And the reason we can do it unchanged is it's using the math kernel library to do an SGEM. And that SGEM code can decide whether a Knights Ferry card's plugged in or not. When it's plugged in, we're showing over a teraflop of performance on this, which is quite a bit more than you would have gotten on just the simple Xeon machine. But the other interesting thing is when you're talking about math algorithms, why not use the Xeon and the Knights Ferry together? And that's the novel approach we have here. In fact, we have a paper here at the supercomputing conference detailing how this was done, but it's using a technique of programming that's sometimes called hybrid programming, where you run part of your problem on one piece of hardware, part on another. In this case, part of it's running on two Xeons, 6 cores each, so 12 cores of Xeon, and part of the problem's being offloaded to a Knights Ferry. And we're able to get over 700 gigaflops of performance by using them together. We would get less than that on if we just use Knights Ferry or we just use Xeon, but in this case we're able to spread the problem across both. So more codes will run on it than you'd expect, but it is very much oriented towards what we'd call highly parallel problems. So what we have is we have a Knights Ferry. We have 32 simpler cores, if you will, all designed together to really result in great speed up on parallel applications. But that said, they're general purpose cores. There's 32 general purpose cores, so we're able to map a number of problems to this that you can't map to what people might call traditional accelerators, because we're not a fixed function pipeline or so forth. We're a bunch of full functioning cores hooked together, and so we're able to handle recursive algorithms. We're able to handle a number of more complex mathematical problems than you typically would expect in an accelerator type piece of hardware. Well, we have a huge amount of flexibility. We support virtually all these different programming models. So OpenMP is one. We'll have support for MPI. We've got different offloading models. The math kernel library knows about it. So it's got that rich environment that you normally would associate with a Xeon environment. We're also using the same tools and methods to program Knights Ferry. They're x86 cores. They're what we would call an in-order design. Some of our processors have out-of-order execution, and that increases the amount of die area, and it's primarily there to run single-threaded applications faster by playing all sorts of games in hardware to run a single-threaded application faster or several single-threaded. Knights Ferry is designed to run parallel workloads, so we don't need that extra hardware, and when we get rid of that and make the processor smaller as a result, we can have more processors on a single die and hook them together in novel ways. That gives us this unique capability. It changes everything. We can use the same tools, things that you're familiar with. The programming models will work. As you'll hear from customers that have been using this, they take codes and in hours it's running on Knights Ferry. They don't have to reformulate the algorithms. And in fact, you can open up a shell and shell into it and do typical commands on it and run the tools logged into Mike itself.